Right, let's dive into today's explainer. I want you to take a quick look at your keyboard. Every single time you type an email, write up a document, or fire off a text, you're actually kicking off a tiny piece of magic. You're pressing a physical plastic key with a human letter printed on it, and somehow, instantly, that keystroke transforms into data. Data that a computer can read, store, and blast across the globe. But how exactly does that happen? Well, today we're unpacking Chapter 25, Appendix D of our source material to understand the invisible dictionary making all our digital communication possible, the International Reference Alphabet.
Here's the roadmap for today. We're covering the language of machines, the International Reference Alphabet itself, how that 7-bit code actually works, the difference between printable and control characters, and finally how we catch errors using something called parity. Let's get to it. Section 1. The language of machines, bridging the text to binary gap. To really get this, we've got to talk about the ultimate language barrier, the one between us and our machines.
Think about it. How does a system built entirely on binary actually read a human word? I mean, we love text, right? Strings of characters, letters, words. It's how we naturally communicate. But our processors, they literally could not care less about the alphabet. They only speak one language, binary, ones and zeros, on and off. So to get these systems to do anything useful with our text, we absolutely had to build a translation bridge.
Now, this isn't exactly a new problem. Way before computers, we still needed to push text through limited communication lines. Remember Morse code? That was probably the earliest common example of converting characters into a coded sequence. We mapped human letters to dots and dashes just to get them across telegraph wires. What we're doing today in modern computing is the exact same concept, just cranked up to a mathematically precise digital level.
Moving right along to Section 2, the International Reference Alphabet, our universal translator, because obviously we aren't using dots and dashes anymore.
Today, we rely on a massive digital dictionary to translate our text, and the standard solution ruling the roost is the International Reference Alphabet, or IRA. It's the most commonly used text code out there, and the concept is brilliantly simple. Every single character you could possibly want to type gets assigned its own totally unique binary sequence. No duplicates, no confusion.
There's a really fascinating footnote in the source text about the naming here. Historically, the IRA was known as International Alphabet Number 5. But here's the kicker for those of you in the US. The American national version of the IRA is widely known as ASCII. Yeah, the American Standard Code for Information Interchange. So if you've ever heard developers throwing around the term ASCII text, well, they're talking about this exact same universal translator. It's the whole shebang.
Okay, Section 3, cracking the 7-bit code and mapping the dictionary. Let's look under the hood and see how this dictionary actually works.
The magic number here, it's 7. The entire International Reference Alphabet is built on a 7-bit binary code. That means every single character we use is represented by a string of exactly 7 ones and zeros, always 7.
And because we're locked into those 7 bits, the math sets a hard limit. 2 to the power of 7 is 128. So that means the IRA can represent a total of exactly 128 unique characters. That is the absolute maximum size of our digital dictionary. Period.
Take a look at this. This is the master map from the text. It might look a bit overwhelming at first glance, but it elegantly shows exactly how every single one of those 128 characters maps out to its unique 7-bit binary sequence. It's like a giant puzzle, fully solved.
So, how do we actually read this thing? Well, the bits are labeled in a very specific order. You always start from the most significant bit. That's labeled B7. And you read your way down to the least significant bit, which is B1. Once you string those 7 bits together in order, boom, you've got your match.
Let's make this concrete. Say you hit a capital K on your keyboard. You aren't actually sending a picture of a K to the processor, right? Instead, the system uses the table to pull a very specific sequence, 1001011. So every time your computer sees 1001011 in a text file, it knows, absolutely for sure, that it needs to display a capital K. It's wild when you think about it.
That brings us to Section 4, printable versus control characters, or what I like to call the seen and the unseen.
So those 128 characters we just mapped out, they actually do vastly different jobs. We can basically split the entire IRA alphabet right down the middle into 2 distinct families, printable characters and control characters.
The difference is pretty straightforward.
Printable characters are exactly what they sound like. The alphabetic, numeric, and special characters you literally see on your screen or print out on paper. Your A's, your B's, the number 4, the $sign. Control characters, though, those are the unseen workers. They're basically hidden instructions. Some of them manage the actual formatting of the text, while others handle the communication procedures entirely behind the scenes. Looking at the control characters here, you'll spot some fascinating everyday examples, like CR. That stands for carriage return, which is actually a really cool throwback to literal, physical carriages on old typewriters. When you hit the Enter key to start a new line, you're actually sending this specific control character. It silently commands the cursor to jump all the way back to the starting position of that same line. You never see the character itself, but you absolutely see its effect.
All right, final section. Section 5, Catching Errors with Parity, the climax of communication. This is where it gets really clever.
So we've got our human text perfectly translated into a 7-bit sequence. Great. But the moment we try to transmit that data over a network, we run into a massive new problem. Networks aren't perfect, right? There's electrical noise, signal degradation. So what happens if a transmission error changes just a single bit during delivery? I mean, if even one binary 1 flips to a 0 as it travels, the whole 7-bit sequence changes. That means an entirely wrong character gets pulled from the dictionary on the receiving end. A crucially yes could instantly become a garbled mess of typo characters.
Engineers knew this was a huge risk, so they came up with an ingenious workaround. In the real world, IRA-encoded characters are almost never transmitted using just those 7 bits. Instead, they're stored and transmitted using an 8-bit block, which we call an octet. They take the 7 bits of the character and they slap an 8th bit right at the front. This most significant bit, labeled B8, is reserved solely as a parity bit. Its only job? Error detection.
Here's how parity actually works in practice. The system automatically sets that 8th bit to either a 1 or a 0 to enforce a strict mathematical rule across the whole 8-bit octet. Systems will use either odd parity or even parity. If it's using odd parity, it sets the parity bit to make sure that when you count up all the binary 1s in the sequence, the total is always an odd number. If it uses even parity, well, you guessed it, the total number of 1s must always be even.
Because of this brilliantly simple rule, catching errors is instantaneous. Let's say your system is running even parity. It receives an 8-bit octet, counts up the 1s, and gets an odd number. Uh-oh, it immediately knows that at least 1 bit flipped during transmission. The parity is broken, so the data is corrupted. This method successfully catches any transmission error that changes a single bit or any odd number of bits.
It's honestly a masterclass in elegant system design. So the next time you hit send on a message, take a second to appreciate the incredible error-catching binary ballet happening right beneath your fingertips. 7 bits to define the letter, 1 bit to protect it. Pretty amazing, right? And it really makes you wonder, what other hidden, deeply structured languages are quietly running the digital world we rely on every single day? Thanks for joining me on this explainer. Keep wondering, and I'll see you next time.